Welcome to lecture 13. This is a kind of unusual lecture because in this lecture I want to show you how to use a computer manipulation package to calculate things like the Christoffel symbols. There are many of these packages available. The one that I'm most familiar with is a Mathematica package. So I'll distribute a Mathematica file to you. So I have it here on my desktop, which we can open up. And I want to show you how to use this particular version of a symbolic manipulation package. And that's something that basically you can get publicly from the web. And I'll also will put the link on the course webpage so you can actually use this. So now how do we actually use this in practice? Let me do this now. Let me sort of go over to the right file here. So basically you have the code up here in this part of the Mathematica file. In practice, you will not need to do anything in here. You can just keep it closed and you can just evaluate this expression with the usual Mathematica command that you press Shift Enter for this part of the code that will load the package, and then you're good to go. How do we actually do the calculation? Well, the magic command here is called rg tensors, and it will need a metric g and some coordinates. So we can get the metric and the coordinates. So for instance, if we want to do this in Mathematica as well, we can define our old coordinates x and polar coordinates to be just x and y. So we have r cosine phi, r sine phi for the coordinates x. The coordinates x prime should be r phi. And then we can calculate the transformation matrix R from the transpose of the derivatives d of x with respect to the first new coordinate, x with respect to the other new coordinate. We can have a look at R and verify that this is indeed a transformation matrix. So that's half of what we already need in order to calculate the metric in polar coordinates, for instance. The other thing we need is the metric in two-dimensional Euclidean space. That's just the Kronecker delta. So I'll denote this metric as unit 2 for the two-dimensional unit matrix. And it should have the following form. That's my unit matrix. And once I have this old metric, I can write the new metric G as the transpose of the transformation matrix dotted into the old metric, dotted into R. And we want to simplify this expression. And what you find is that this indeed is the metric in the polar coordinates that we need. So now we have the metric G and we have the coordinates. So now let's work our magic and calculate all sorts of things. So that's what happened if you evaluate this command rg tensors. It says that the metric that you wanted it to use is this metric here. D, little d here stands for downward indices, whereas up stands for upwards indices. So GDD is just G mu nu with downwards indices, whereas GUU is the metric with upward indices. That's the inverse matrix. It also tells you the line element for this metric, ds squared, which is r squared d phi squared plus dr squared. And then it tells you how quickly you could calculate the inverse metric. Then it tells you that they calculated gamma, which are nothing else but the Christoffel symbols that we're after. And then it calculates other stuff as well, such as the Riemann tensor, which we haven't learned yet in this course, but we'll need eventually when we calculate more complicated things in GR. It also tells you that this is flat space because that's what it is. So now that we have issued this command, we can access some of these symbols the following way. So for instance, if you want the inverse metric, you just want to access the symbol GOU. Again, we can write this in matrix form. It looks like this. Or if you want to access the Christoffel symbols, the relevant command is G up, down, down for Christoffel symbol with first index up and the other two down. So that's G mu upstairs, alpha beta downstairs. And that is a 2 by 2 by 2 matrix. Many of these components are 0, but we know that some of them are not. So for instance, the one that we calculated was G up down with the first index being R. So in our notation, the first index being R corresponds to the first entry of the coordinates. So it's G up, down, down from 1. So basically this is G R R R. This is G R R phi, G R phi R, and G phi phi. So that means that G, particular G R, this is Christopher symbol upwards, down, down. The upward index should be R, so that's 1. On the 2 lower index should both be phi, so that's 2, 2. And that's the Christopher symbol that we've calculated. Similarly, we can look at all Christopher symbols with upward index phi. We can find that there's only some of them which are non-vanishing, and you can tell that this one should be the one where one of the downstairs indices is R and the other one is phi. So that's GR R phi, which is equal to GR, which is equal to GR phi R because of the symmetry in the low indices. So that is the other non-vanishing Christopher symbol. So that is basically what we have used this package for. Of course, we can do more complicated examples. So let me do a more complicated example by saying that I want to copy this and do, for instance, spherical coordinates. Then what I have to do is slightly modify this expression here. So instead of R cosine phi, R sine phi, this would be R cosine phi sine theta, R sine phi sine theta for y, R cosine theta, if the coordinates are R, theta, and phi. So these would be spherical coordinates. Then our matrix, transformation matrix, would be the same, except that there is a derivative of R with respect to, or coordinates with respect to theta missing. This would be our transformation matrix for 3-dimensional spherical coordinates. We now need the Kronecker delta in 3 dimensions, which we can simply get from the Kronecker delta in 2 dimensions by just adding 1 dimension to the matrix. So this should be a 3-dimensional matrix. And then the new metric should be the old metric transformed, and that is, or should be, the metric in spherical coordinates. So that's how we get it. And then we can again do our magic and just let the program calculate all sorts of things. So for instance, it calculates the inverse metric, and it calculates the Christopher symbols for this 3-dimensional example. Again, it recognizes that this is again flat space, which it is. It's just flat space expressed in spherical coordinates. So for instance, we can look at G up by evaluating this expression. Then the Christopher symbols, of which there are now 3 by 3 by 3, 27, look like this. These are all of them. And you can evaluate the one that have an R upstairs. So get rid of those. The one that have theta upstairs, and the ones that have a phi upstairs. You get all Christopher symbols. And again, the main point is that this just simplifies your life because you don't need to spend hours to calculate all these entries. It just basically can be done via this symbolic manipulation package. And that concludes the demonstration. Again, I will upload this to the web page so you can find it there.